this demo on working with Cluster Autoscaler add-on. I am Mahendra Mehra, your senior OCI instructor with Oracle University. In this demo, we'll be diving into the functionality of the Kubernetes Cluster Autoscaler, specifically focusing on its role as a cluster add-on. Let's dive in. During our demo, we'll be walking through a series of essential steps to effectively work with the Kubernetes Cluster Autoscaler add-on. To start with, we will be creating a dynamic group to allow nodes running the Kubernetes Cluster Autoscaler to manage node pools referenced in the Cluster Autoscaler add-on configuration. In the interest of time, I've already created the dynamic group. Now let me showcase what we have set up. I'll be transitioning to the OCI console. I've already logged into my OCI console. I'll take you to the dynamic groups page. I'll click on the hamburger menu, go to identity and security, and click on domains. I'll select my root compartment here and go to the default domain. I'll select dynamic groups from the left menu. And here I've already created a dynamic group named Acme OKE Cluster Autoscaler Dynamic Group. I'll select it. As you can notice, this dynamic group is for all the instances running in the compartment with the OCID as given on the screen. And this is the OCID of my compartment CTD OKE. Let's head back to the slide deck. The next step is to create policy to allow worker nodes to manage node pools. We have already created a dynamic group for all our worker nodes running in the CTD OKE compartment. Now we'll be creating the policy to allow these worker nodes, or indirectly the dynamic group, to manage all the node pools within the compartment CTD OKE. Again, in the interest of time, I've already set those policies. Let me show it to you. I'll click on the hamburger menu, go to identity and security, and click on policies. I'll select the parent compartment for my CTD OKE compartment, which is Mahendra. And here I've already set up the policies for our dynamic group. I'll click on the policy. These are the policies that you must set to allow your worker nodes to manage the node pools. The policy is to allow dynamic group, the name of our dynamic group, which is Acme OKE Cluster Autoscaler Dynamic Group, to manage cluster node pools in compartment CTD OKE. The other set of policies are to manage instance family, use subnets, read virtual network family, use VNix, and inspect compartments in the compartment CTD OKE. Next step is to enable the add-on on the Kubernetes cluster, where we want to set up the cluster autoscaler. I'll head back to the OCI console and go to the Kubernetes service page. Let me select the navigation menu, click on developer services, and click on Kubernetes clusters. I'll select the CTD OKE compartment, and here and from the list of clusters in my CTD OKE compartment, I'll be selecting the OCI OKE CA demo cluster for this demonstration. On the cluster, I'll scroll down to the resources section and click on add-ons. And currently we don't have the cluster autoscaler add-on enabled. I'll click on manage add-ons button. And if we scroll down, we have the cluster autoscaler add-on available, which is currently disabled. I'll select this option and I'll check the enable cluster autoscaler add-on. We get to choose from the two options. One is the automatic updates, where Oracle manages the automatic updates of this add-on on your cluster, or else we can opt for choose a version option, where we select the version manually from the drop down. There are 3 versions available for the current cluster version. I'll stick to the automatic updates. Now let's populate the parameters for the cluster autoscaler add-on. The first parameter we'll populate is nodes. Nodes parameter basically specifies the node pool to automatically resize, and to specify the minimum and maximum number of nodes in each node pool, we must use the following format. The format is minimum number of nodes, colon separated by maximum number of nodes, and colon separated by the node pools OCID. And if we have multiple node pools to manage through the cluster autoscaler, then in that case we must use comma separation and specify the same format for the other node pools in your Kubernetes cluster. So this is the format in which we specify the value for our nodes parameter, where the minimum nodes value is the number of nodes allowed in the node pool. The Kubernetes autoscaler will not reduce the number of nodes below this number. In our case, I've specified it as 2. And the max nodes value is the maximum number of nodes allowed in the node pool, where the Kubernetes cluster autoscaler will not increase the number of nodes above this number. In our case, it is set to 5. And then here I've specified the OCID of our node pool, which the Kubernetes cluster autoscaler will manage. Now, how do you get the node pool's OCID? You go to the cluster's detail page. I'll select the cluster first and go to the node pools section. Click on the node pool name and copy the node pool OCID from the node pools detail page. I'll go back to the notepad file and replace this OCID with the OCID of our node pool. Copy the entire string and go back to the first tab and paste the value in this box. I'll go ahead and configure the next parameter, which is the number of replicas. Remember from the lesson that we must always define multiple replicas for the Kubernetes cluster autoscaler deployment, which is why I'll set it to 3. I'll add another parameter to the Kubernetes cluster autoscaler configuration, which is maximum node provision time, and I'll set it to 25 minutes. I'll go ahead and click on Save Changes. And as we can observe, the cluster autoscaler add-on is now enabled. I'll click on Close. And the entry for the cluster autoscaler is now present in the add-ons section, and the status says ready. Now, once the cluster autoscaler add-on is enabled, the next step is to verify the autoscaler status. To view the status of the Kubernetes cluster autoscaler pods, we can use the kubectl get pods command, and these pods run within the kube system namespace. I'll head back to the OCI console. On the next tab, I've already opened up the Cloud Shell terminal. I have already set up the cluster access to our Kubernetes cluster. I'll run the kubectl get nodes command. The cluster that I'm using for demonstration has one node pool running 2 worker nodes within it. Confirm the same. If I go to the node pools section, there is one node pool running 2 worker nodes within it. Now, to view the status of Kubernetes cluster autoscaler pods and observe progress of the deployment, we can run the kubectl get pods command. The command is kubectl get pods -n kube system. The cluster autoscaler pods run within the kube system namespace, and we are piping it to the grep operator to select only those pods that are titled as cluster autoscaler. I'll go ahead and hit enter. And if you recollect, we had set number of replicas to 3 for our cluster autoscaler, which is why we can see 3 pods of cluster autoscaler running in our Kubernetes cluster. Now, to view the Kubernetes cluster autoscaler logs, just to confirm that the add-on was successfully deployed and is currently monitoring the workload of the node pool that we had defined within the configuration, we must run the kubectl logs command. The command is kubectl -n kube system logs, and we are fetching the logs for the deployment of our Kubernetes cluster autoscaler. I'll go ahead and hit enter. And from the output, we can confirm that the Kubernetes cluster autoscaler is successfully deployed and is currently monitoring the workload of our node pool. I hope you're enjoying the demo so far. See you in the next one. Thank you for watching. Hello and welcome to this lesson on Kubernetes metrics server overview. I am Mahendra Mehra, your senior OCI instructor with Oracle University. Let's get started. Picture the metrics server as the central hub aggregating resource usage data from each worker node's kubelet. This valuable data is then exposed through the Kubernetes metrics API. Now let's explore the crucial connections extending from the metrics server in our diagram. This represents the vital links to other Kubernetes add-ons. The horizontal pod autoscaler. It utilizes this data to dynamically adjust the number of pods in a deployment, ensuring optimal resource usage. On the other hand, the vertical pod autoscaler, also known as VPA, leverages the metrics server to fine-tune the resource request and limits for containers running in a deployment pod. Let's highlight two critical aspects of the Kubernetes metrics server. First, its versatility, compatible with both managed node pools and virtual node pools, offering you choices in deployment. Second, essential to understand that the metrics server is purpose-built for autoscaling. While it excels in this role, it's not recommended for forwarding metrics to monitoring solutions or serving as a standalone source for monitoring metrics. With this, we come to the end of this lesson where we quickly got an overview about the Kubernetes metrics server. I hope you found this lesson useful. See you in the next one. Thank you for watching. Hello and welcome to this demo on deploying the Kubernetes metrics server on a cluster using kubectl. I am Mahendra Mehra, your senior OCI instructor at Oracle University. Let's get started. Well, let's look at the steps required to deploy the Kubernetes metrics server. Firstly, we must set up the cluster access using the kubeconfig file. For this demonstration, I've created a Kubernetes cluster named OKE metrics server demo. I'll use this for our demonstration. I'll go ahead and click on the cluster name. To set up the cluster access, I'm on my cluster details page and I'll click on the access cluster button. I'll copy the command provided for the Cloud Shell access. I'll go to the next tab where I've already opened up the Cloud Shell terminal and paste the command, hit enter, and the cluster access has been set up. I'll run the kubectl get nodes command. Well, it has returned the worker nodes running in our Kubernetes cluster. I'll close this window. Go to the node pools section, click on the pool name and confirm the IPs which are ending with 198, 188 and 71 are the same that has been retrieved when we ran the kubectl get nodes command. This is just to verify that I'm connected to the right Kubernetes cluster. Well, this node pool is a managed node pool. Remember that the Kubernetes metrics server can also be installed on virtual node pools. For this demonstration, I'll stick to managed node pools. Now the next step is if your Oracle Cloud Infrastructure user is a tenancy administrator or cluster administrator, we can skip this step. But if your OCI user is not a tenancy administrator or cluster administrator, then you must ask your tenancy administrator or cluster administrator to grant the user the Kubernetes RBAC cluster admin cluster role on the cluster. And to do that, you can use the kubectl create cluster role binding command, specify the name to the binding and set the cluster role flag to cluster admin. Also specify the user flag and provide the user's OCID. In our case, the user using which I'm running this demonstration is already an administrator. So I'll skip this step. The user OCID is available under the user's profile menu. You can click on the profile menu on the top right and click on my profile. And under the user information tab, you can simply copy the OCID and use it in the command. Now, if you are going to deploy the Kubernetes metric server on a cluster with managed node pools, deploy the Kubernetes metric server by entering the following command in the terminal. You should use the kubectl apply command and use the URL as given on the screen. But remember that the version number is the Kubernetes metric server version that we want to deploy. For example, version 0.6.1. But note that since the Kubernetes metric server is being actively developed, the version number to specify will change over time. And to find out the currently available version, you should visit the GitHub URL, which is this. As you can see from the URL, the current Kubernetes metric server version is 0.6.4. You can use this command to set up the Kubernetes metric server on our managed node pool. I'll copy this command and head back to the Cloud Shell terminal and paste the command here. I'll go ahead and hit enter. Well, all the required resources have been created for the Kubernetes metric server. Now we must confirm that the Kubernetes metric server has been deployed successfully and is available. To confirm the same, we can use the kubectl get deployment metric-server command and specify the namespace as kube-system. I'll go ahead and hit enter. And as we can notice, the metric server is up and running. And like I mentioned, that you can install Kubernetes metric server on a cluster with virtual node pools also. And in order to do so, you must go to the following URL in the browser and download the manifest file, that is components.yaml, to your local machine. Remember, you must provide the latest version number for your Kubernetes metric server. Now, once you download the components.yaml manifest, you must remove the liveness probe and readiness probe section from the manifest of the metric server deployment. I've already downloaded the components.yaml manifest. Let me bring it up for you. This is the component.yaml manifest used to deploy the Kubernetes metric server. Scroll down and locate the liveness probe and readiness probe section. As you can notice on the screen, this is the liveness probe section that you must delete, as well as the readiness probe section. Save the components.yaml manifest file after editing on your local machine and run the kubectl apply command to deploy the Kubernetes metric server on your Kubernetes cluster running virtual node pools. To confirm that the Kubernetes metric server has been deployed successfully and is available, you must enter the command kubectl get deployment metric server and specify the namespace by using -n. The namespace is kube system. The output will confirm whether the metric server is ready or not. As in our case on the managed node pool, the metric server was successfully deployed. With this, we come to the end of this demo where we successfully deployed the Kubernetes metric server on the container engine for Kubernetes cluster using kubectl. I hope you found this demo interesting. See you in the next one. Thank you for watching. Hello and welcome to this lesson on Kubernetes Horizontal Pod Autoscaler. Let's get started. Kubernetes Horizontal Pod Autoscaler is a powerful tool for automating pod scaling in your Kubernetes cluster. To unleash its potential, you'll need to install a metrics source such as the Kubernetes metric server in your cluster. As you engage with the Horizontal Pod Autoscaler, you gain the ability to dynamically adjust the number of pods in your deployments, replication controllers, replica sets, or stateful sets. This adjustment is intelligently driven by factors like CPU, memory utilization, or other metrics, allowing your applications to seamlessly scale out during periods of high demand or scale in when resources are no longer needed. Adding precision to your scaling strategy, you can set target metric percentages for the horizontal pod autoscaler to meet when scaling your applications. The flexibility doesn't end here. If your scaling needs extend beyond CPU and memory utilization, alternative implementations of the Kubernetes metrics API support scaling based on custom metrics. While the horizontal pod autoscaler brings automation, it's important to note that manual scaling options are also available. You can manually scale applications by updating manifest files without relying on the horizontal pod autoscaler. Whether you are working with managed node pools or virtual node pools, the Kubernetes horizontal pod autoscaler seamlessly integrates into your Kubernetes environment, providing a versatile and efficient scaling solution. Stay tuned as we explore the hands-on demonstration, unraveling the functionalities and configurations of the horizontal pod autoscaler in Container Engine for Kubernetes in our next video. Thank you for watching. Hello and welcome to this demonstration on working with the horizontal pod autoscaler, a powerful tool that enables automatic scaling of the number of pods in response to different workloads. Let's get started. There are different steps in which we'll be performing this demonstration. For the horizontal pod autoscaler to work, we need to install Kubernetes metrics server. The first step would be to verify that the Kubernetes metrics server has been installed on the cluster or not. I will head to the OCI console, and in the OKE cluster that we are using for this demonstration, let's quickly check the metrics server status. I'll first visit the cluster that I'll be using for this demonstration. I'll click on the Kubernetes clusters link from the recently visited section. OKE metrics server demo is the cluster we'll be using for this demo. I'll click on the link. This is a cluster running with one managed node pool. And the managed node pool is operating with 3 worker nodes. On a separate tab, I have opened up the Cloud Shell terminal, and here I'll run the command kubectl-n kubesystem get deployment/metrics server. The output of this command will confirm the installation of metrics server on this cluster. Well, the output confirms that the metrics server has been installed on this cluster. As we can see from the ready column, there's one pod of metrics server running on the Kubernetes cluster. We have already covered installation of metrics server on an OKE cluster in our previous demo. To demonstrate a horizontal pod autoscaler, we will first start a deployment that runs a container using the horizontal pod autoscaler example image and expose it as a service using a manifest file. To deploy the sample application, we can run kubectl apply -f and the URL to that sample application, which is available as part of the Kubernetes examples. But in our case, I've downloaded the PHP Apache manifest on our local machine. I'll open up the manifest for you. Let me clear the screen and navigate to my examples directory. Here is the manifest that I have downloaded from the same URL I showed you in the earlier command. Now I'll open up the manifest file. Well, from the manifest file, it's clear that it's creating a deployment with the name PHP Apache. And from the containers section, we can confirm that it's pulling an image from the registry.k8s.io repository. And the name of the image is HPA example. And the container port 80 has been exposed. Now under the resources section, make a note that the CPU limit has been set to 500 millicores, which ensures that the container will never use more than 500 millicores or half of a core. And the request allowance is set to 200 millicore, which allows the container to use 200 millicores of CPU resources or 1/5 of a core. At the bottom, we have the service section defined to expose the deployment PHP Apache using cluster IP on port 80. We'll close this manifest file and go ahead and deploy this manifest on our Kubernetes cluster using the kubectl create command. I'll hit enter. Well, the deployment and the service PHP Apache has been created. Now if I run kubectl get all command, you can notice that the PHP Apache pod is up and running, as well as the service PHP Apache of type cluster IP is up and running. Pod PHP Apache is part of the deployment PHP Apache with the replica set where the desired count for the pod is set to 1. Now the next step is to create a horizontal pod autoscaler resource that will scale based on CPU utilization. I'll clear the screen, and to run the autoscaler I'll use the command kubectl autoscale deployment and the name of deployment, which is PHP Apache, and I'm setting the CPU percentage to 50 and the min count is set to 1, whereas the max count is set to 10. With the help of this command, I'll create a horizontal pod autoscaler resource to maintain a minimum of 1 and maximum of 10 replicas and an average CPU utilization of 50%. I'll go ahead and hit enter, and the output says horizontal pod autoscaler PHP Apache has been autoscaled. What this autoscaler would do is it would maintain a minimum of 1 and maximum of 10 replicas of the previously created pods controlled by the Apache web server deployment. It increases and decreases the number of replicas of the deployment to maintain an average CPU utilization of 50% across all pods. Remember, if the average CPU utilization falls below 50%, the horizontal pod autoscaler will try to reduce the number of pods in the deployment to the minimum, which in this case is 1. And if the average CPU utilization goes above 50%, the horizontal pod autoscaler will try to increase the number of pods in the deployment to the maximum value. And in this case, we have set it to 10. Let's check the current status of horizontal pod autoscaler by entering the kubectl get HPA command. I will hit enter. The output of the kubectl get HPA command shows the current status. The target column shows the average CPU utilization across all pods controlled by the Apache web server deployment. Now, since there are no traffic being sent to the server, the output shows the current CPU utilization as 0% compared to the target utilization of 50%. Next step is to generate load. We will see how the autoscaler reacts to increased load. And to do this, we will start a different pod to act as a client. The container within the client pod runs in an infinite loop and sends queries to the PHP Apache service. Let's head back to the OCI console and start generating load. Using the kubectl get svc command, I'll grab the cluster IP address of the PHP Apache service. Now I will use the kubectl run command to generate load using the client pod that is running busybox image. And the script here is executing while loop where we are continuously sending traffic to the cluster IP, which is running the service that is exposing the PHP Apache deployment. I'll go ahead and hit enter. As you can notice, the requests are being sent to the cluster IP that is exposing our PHP Apache deployment. Now that we have started generating load, it's time to view the scaling operation in action. Let's head back to the OCI console. I will switch to a new terminal and run the kubectl get HPA command. I'll supply the watch flag. We'll notice that the CPU utilization across all pods controlled by the Apache web server deployment is above 50% at the start, and the horizontal pod autoscaler is trying to bring it to 50%, for which it is trying to create new replicas of the pod running the PHP Apache web server. From the output, we can notice that the horizontal pod autoscaler has resized the deployment from 1 replica to 5 replicas and then to 7 in order to get the utilization target of 50%. Make a note that one might see different numbers depending on how long they wait before running the command. For us, it has scaled to 7 replicas where it could meet the utilization parameter of maintaining 50% across all pods. I'll quit the command here and clear the screen. Now to verify that the deployment has been scaled out, I'll run the command kubectl get deployment. And we can observe that the PHP Apache deployment has been scaled out and there are 7 pods running for the PHP Apache web server. Now I'll go to the previous tab and stop generating the load. I'll press Ctrl C here and this has stopped generating the load. I'll go back to the next tab and we will see the status of horizontal pod autoscaler after we have stopped generating the load. Run the command kubectl get HPA and provide the deployment name, that is PHP Apache. Hit enter. I'll use the watch flag here. We'll notice that the CPU utilization has reduced to 0%. However, we can still see 7 replicas in the deployment. Just a note that you will see different numbers depending on how long you wait before running the kubectl get HPA command after the load generation has stopped. Also be aware that it will take some time for the replica count to reduce to 1. 5 minutes is the default time frame for scaling in. Notice that after a while the horizontal pod autoscaler is trying to scale in the number of pods as the CPU utilization has decreased. Now we can notice that the number of pods running for the PHP Apache deployment is reduced to 1. I'll quit this command and we will run the kubectl get deployment command. And we can confirm from the output that the number of pods have reduced from 7 to 1 after the load generation was stopped. Now to perform cleanup, I'll use the kubectl delete command to delete the horizontal pod autoscaler. I'll go ahead and hit enter. And the output says the PHP Apache horizontal pod autoscaler was deleted. With this, we come to the end of this demo where we saw in action how the Kubernetes horizontal pod autoscaler automatically scales the number of pods on a container engine for Kubernetes cluster. I hope you found this demo interesting. See you in the next one. Thank you for watching. Hello and welcome to this lesson on Kubernetes vertical pod autoscaler. Let's get started. Firstly, the vertical pod autoscaler automates the adjustment of resource requests and limits for containers in your deployment's pods, providing an intelligent and automated solution for optimal resource utilization. This tool enhances your cluster's resource efficiency by dynamically setting requests based on pod usage, ensuring that the appropriate resource amounts are available for each pod. It also maintains the specified ratios between limits and requests, aligning within the container's initial configurations. For efficient scaling, the vertical pod autoscaler scales down pods that over-request resources, analyzing their historical resource usage. On the flip side, it scales up pods that under-request resources, adapting to their usage patterns over time. The vertical pod autoscaler operates through 3 key components. The recommender monitors current and past resource consumption, providing recommended CPU and memory request values. The updater identifies pods with incorrect resources, deletes them, and recreates them with updated request values. And the admission plugin sets correct resource requests on new pods created or recreated by their controller. To configure the vertical pod autoscaler, you'll use the vertical pod autoscaler custom resource definition object. This enables you to specify the pods for vertical autoscaling and define resource recommendations as needed. It's important to note that the vertical pod autoscaler requires the installation of a metric source in the cluster, such as the Kubernetes metric server, to function properly. This dependency ensures accurate monitoring and adjustment of resources. Stay tuned as we explore hands-on demonstrations unraveling the functionalities and configurations of the vertical pod autoscaler in Container Engine for Kubernetes. I hope you found this video useful. Thank you for watching. Welcome to our lesson on upgrading clusters to newer Kubernetes versions. In this video, we'll explore the process of upgrading your Kubernetes version on control plane nodes and worker nodes within an OKE cluster. Let's get started. When you create a new Kubernetes cluster by using Container Engine for Kubernetes, you have the flexibility to specify the version of Kubernetes for both the control plane nodes and the worker nodes in the cluster data plane. Notably, within a single node pool, you can even have different worker nodes running different versions of Kubernetes. Additionally, if your cluster comprises multiple node pools, each node pool can operate on its own distinct version of Kubernetes. Let's explore these customization options further. Let's explore the dynamic world of Kubernetes versions. Kubernetes project frequently releases new versions, each bringing a mix of fresh features, updates, and bug fixes. These versions are uniquely identified by a three-part format: X.Y.Z, where X represents a major release, Y is a minor release, and Z signifies a patch release. For instance, we might have a version like 1.27.2. It's worth noting that there is a relationship between the versions on worker nodes and control plane nodes. The Kubernetes version on the worker nodes can lag behind the control plane nodes by up to 2 versions or 3 versions starting from Kubernetes version 1.28. However, exceeding this lag renders the version incompatible. As shown in the graphics, if the control plane node is running on version 1.27.2 and the worker nodes are running on version 1.27, which is similar to the one running on control plane, or 2 versions behind, which is 1.26 and 1.25, they are compatible. But if the gap increases by 2, as shown in the graphics here, where the version of the worker node is 1.24.1, in this case, they become incompatible. Also, a point to note is that the versions on worker nodes must not be more recent than the versions on the control plane nodes. As shown in the graphics here, if your worker node is running version 1.28 and the control plane is running version 1.27, in this case, they both become incompatible. A worker node should never be running version greater than your control plane node. Let's navigate through the key points. Firstly, Kubernetes embraces version diversity, allowing control plane nodes and worker nodes to gracefully run different versions, all within the bounds of the Kubernetes version SKU support policy. Now, the upgrade journey begins. Upgrading control plane nodes involves elevating the entire cluster to a new Kubernetes version. During this orchestrated upgrade, control plane nodes running older versions undergo an automatic and graceful transformation to align with the upgraded cluster. One notable feature is the zero downtime during the upgrade process. Thanks to the high availability distribution of control plane nodes, this ensures uninterrupted service availability for your applications. Post-upgrade, you have flexibility. Create new node pools with your worker nodes sporting the latest version or continue with existing ones provided they are compatible with the upgraded control plane version. In conclusion, upgrading control plane nodes in Kubernetes is a meticulous and smooth operation, providing you with flexibility and ensuring minimal disruption to your running applications. I trust you found this lesson insightful. See you in the next one, and thank you for watching. Hello and welcome to this short demo on upgrading clusters to new Kubernetes versions. I am Mahendra Mehra, your senior OCI instructor at Oracle University. Let's get started. I'll transition to the OCI console. I'm already logged into my OCI console and I'll go to the Kubernetes clusters service page. I'll go through the recently visited links. The cluster which I'll be upgrading is the OKE public demo 2 cluster. I'll select this cluster. Now, as we discussed in the lesson, if a newer Kubernetes version than the one running on the control plane nodes in the current cluster is available, the new Kubernetes version available button is enabled at the top of the cluster's details page. Now, to upgrade the control plane nodes to a newer version, I'll click on this button. And any new information regarding the current update is provided on this window. As you can notice, the pod security policies will be disabled from version 1.25 onwards. And also, if you upgrade your cluster's control plane, you cannot downgrade it. So it's always recommended that you test the applications deployed on the cluster to see if they are compatible with the newer Kubernetes version. Now, to upgrade the cluster control plane, I'll select the drop down from the Kubernetes version field, and as you can notice, we have the upgraded version available, which is version 1.28.2. I'll select this version and click on upgrade. Once we click on upgrade, the cluster will enter in updating state. As you can see on the screen, the cluster is now in the updating state. You can check that through the work request section. As you can notice, the cluster update operation is in progress. In the meanwhile, a quick information that when you upgrade the Kubernetes version running on the control plane nodes, the virtual nodes in every virtual node pool in the cluster are automatically upgraded to that Kubernetes version. This cluster is running managed node pools, but if your cluster is running virtual node pools, it's an important piece of information to have. Notice the current Kubernetes version is 1.27.2. This will change after the update process to 1.28.2. Well, after some approximately 7 to 8 minutes, the Kubernetes control plane has been upgraded to version 1.28.2. Once the Kubernetes version running on the control plane node is upgraded, the new Kubernetes version appears as an option when you are defining new node pools for the cluster. Let me show this to you in action. I'll go to the node pools section, click on add node pool. And if you notice, the worker nodes in the node pool are still running on the previous version, which is 1.27.2. But if we go ahead and create a new node pool now, we will have the option to choose the latest version. And if you notice in the version field, we can choose from all of these versions that are available. And as discussed in the lesson, from version 1.28 onwards, the worker nodes can lag by 3 older versions, which is why we have the option to choose Kubernetes version up till version 1.25.4. I'll click on cancel. We can also edit the properties of our existing node pool so that any new node added to the existing node pool can run on the latest Kubernetes version. I'll click on the existing node pool, and here I'll click on the edit button. This opens up the edit node pool page, and under the versions field, from the drop down, we can select the latest version, that is version 1.28.2, which is the current cluster version. And as the information reads, it says node added to this node pool will run the upgraded version, which means any new nodes added to this node pool will be running Kubernetes version 1.28.2. For instance, if I add a new worker node to this node pool by increasing the node count to 4 and click on Save Changes, the node pool has gone into updating state. And in some time, we will see a new node entry here under the nodes section, which will have the Kubernetes version running 1.28.2. Well, as you can see, the node entry is created. Currently, it's in the creating state, but we can observe that the version running on the worker node is 1.28.2, which is one version ahead as compared to the Kubernetes version running on the previous worker nodes in the same node pool. After a while, our new node is now in the ready condition and in an active state, running the Kubernetes version 1.28.2. With this, we come to the end of this demo where we saw how to upgrade the Kubernetes clusters control plane node in OCI Container Engine for Kubernetes. I hope you found this demo useful. See you in the next one. Thank you for watching. Hello and welcome to this lesson on upgrading the Kubernetes version on worker nodes in a cluster. Let's get started. It's important to note that managed nodes, self-managed nodes, and virtual nodes follow distinct upgrade paths. Let's dive into the details. When it comes to upgrading managed nodes, there are various approaches. You can choose an in-place upgrade of a node pool where specifying a newer Kubernetes version initiates an automatic cycle, seamlessly replacing each worker node. Alternatively, opt for an in-place upgrade with manual replacement, allowing more control by replacing each existing worker node with a new one configured for the updated Kubernetes version. Another option is an out-of-place upgrade, where you replace the original node pool with a new one specified for a more recent Kubernetes version. For self-managed nodes, the upgrade involves replacing an existing self-managed node with a new one hosted on a different compute instance. This process ensures a smooth transition to a new Kubernetes version, providing you with control over the upgrade path. Virtual nodes are upgraded in tandem with control plane nodes. When you upgrade the control plane nodes to a new Kubernetes version, virtual nodes in all virtual node pools are automatically upgraded to the same version. This seamless coordination simplifies the upgrade process for virtual nodes. Let's navigate through the key considerations for a seamless control plane upgrade. Firstly, it's crucial to note that Container Engine for Kubernetes places the power of control in your hands. You explicitly initiate control plane node upgrades when you are ready, ensuring a careful orchestrated process. Now, once you have upgraded the control plane nodes, a critical point to remember is that there's no provision for downgrading them. This emphasizes the importance of thoughtful planning before executing an upgrade operation. Moving on, testing is paramount. Before you embark on the upgrade journey, it's your responsibility to test your applications for compatibility with the new Kubernetes version. This step ensures a smooth integration between the control plane and worker node. As you consider versions, especially if your control plane is a bit behind, the system offers you a choice of versions to upgrade to. It's essential to follow a sequential upgrade path, ensuring a stable transition. Last but not least, ensuring a successful control plane upgrade requires specific conditions. Kubernetes dashboard service must be of the type cluster IP, showcasing the importance of proper service configuration. As we conclude, Keep in mind that the upgrade process varies for managed node, self-managed nodes, and virtual nodes. Understanding these distinctions allow you to tailor the upgrade strategy to your specific environment. Thank you for joining this session and stay tuned for the more valuable insights in our upcoming lesson. Hello and welcome to this demo on upgrading the Kubernetes version on worker nodes in a cluster. I am Mahendra Mehra, your senior OCI instructor with Oracle University. Let's dive in. I'll navigate to the OCI console. I'm already logged into my OCI console and this is my OCI dashboard. I'll go to the Kubernetes cluster service page and click on the first cluster from the cluster list. This is the cluster which we upgraded to the latest Kubernetes version, which is version 1.28.2. I'll go to the node pools section. First up, we will be seeing how to perform an in-place managed node Kubernetes upgrade by manually replacing nodes on existing node pool. Currently, this node pool has 4 worker nodes running within it. From the previous demo, we saw how to add a new worker node to the existing node pool with the updated Kubernetes version, which is why there's one standout worker node running the latest Kubernetes version, whereas the other 3 are still running the older Kubernetes version, which is one version behind the control plane version. First thing that one must do is click on edit button and update the version field to the latest version. If you recollect from the previous demo, for this node pool, we had already selected the latest version. I'll click on cancel. Well, the node pool property was already updated to select the latest version for any new nodes running in this node pool. Now for the in-place upgrade, we will be manually deleting the existing managed nodes so that the new managed nodes are started running the Kubernetes version 1.28.2. Now before that, I'll open up the Cloud Shell editor and I'll show you if there are any pods running within this managed node. For better viewing, I'll duplicate this tab. Well, I'm using the Cloud Shell terminal on a separate tab and I've already configured the cluster access to the Kubernetes cluster that we are working on. I'll run the kubectl get nodes command and it has returned the 4 nodes that are running in our pool 1 on the Kubernetes cluster. As you can notice, the private IPs are ending with 149, 26, 150 and 14, which is what is returned as part of the kubectl get nodes command. Also notice the versions. It's one worker node that's running version 1.28.2, whereas the other 3 are running version 1.27.2. I'll run the kubectl get pods command and use the flag -o wide. Well, if you observe that there are 4 pods running on this cluster on nodes 149, 150 and 26. If you observe, the node 10.0.10.26 is running on an older version and this particular node has 2 pods deployed on it. Now I'll go back to the previous tab and select the node 10.0.10.26. Click on the drop down here and click on the actions menu and click on delete node. I'll click on the show advanced options. I'll accept the default setting for the cordon and drain settings for this worker node, just 60 minutes. Ensure that you do not select this option to decrease node pool size so that the new worker node is started rather than the node pool being scaled down. I'll click on delete. To check if the delete operation is in progress, I'll click on the work request. And as we can see, we have the node pool update operation that is accepted and in progress. The node pool is in the updating state. As can be seen here, the node pool update operation is in progress. I'll go ahead and select the nodes again. And as you can notice, the node 10.0.10.26 is getting deleted whereas a new node has spun and it's in the updating state. Also closely observe that the new node that's getting created is running the latest Kubernetes version 1.28.2. Now we will wait for some time before these operations are completed successfully. Well, after some while, the operations have completed successfully. We have a new worker node that is up and running with the IP 10.0.10.184, running the Kubernetes version 1.28.2. And our previous worker node with the IP 10.0.10.26 no longer exists in the system. As you can see, it's deleted. If I go back to the Cloud Shell terminal and run the kubectl get pods -o white command again, you will notice that the nginx pods that were previously running on 10.0.10.26 are now moved to a different node, that is 10.0.10.14 and 10.0.10.50. And if I run the kubectl get nodes command, you can see that 2 nodes out of the 4 nodes are running version 1.28.2. And this is how we can manually perform in-place managed node upgrades by manually replacing nodes in an existing node pool. We can repeat the same process for the other 2 worker nodes, but for now I'll skip it. An in-place upgrade by cycling the nodes to automatically replace all the existing managed nodes. And to do so, we must click on the cycle nodes button on the existing node pool. I will go ahead and click on the cycle nodes button. Always ensure that before you run the cycle nodes operation, you must edit your node pool property to ensure that the version is selected to the latest Kubernetes version that you wish to configure on the worker nodes running within your cluster's data plane. The container engine for Kubernetes uses 2 strategies when using cycling nodes. One is to create new additional nodes and then remove the existing nodes, and the other one is to remove existing nodes and then create new nodes. The first option maintains the service availability but will cost you more, whereas the second strategy costs less but might compromise service availability. Now, to tailor the container engine for Kubernetes behavior to meet your own requirements for service availability and cost, we can control and balance the 2 strategies by specifying the maximum surge and minimum unavailable options. The number of additional nodes to temporarily allow during the upgrade operation is referred to as maximum surge, and the number of nodes to allow to be unavailable during the upgrade operation is referred to as maximum unavailable. And in both cases, we can specify the allowed number of nodes as an integer or as a percentage of the number of nodes shown in the node pool node count property. If we don't specify a value for either the maximum surge or maximum unavailable, the defaults are used, and the default value for maximum surge is 1 and for the maximum unavailable is 0. In case you are planning to specify a number yourself, do not specify a number greater than the value of the node count that is defined in your node pool property. I'll set the max surge value to 2 and maximum unavailable to 2 and click on cycle nodes. Well, the node pool is now getting updated. As you can see, there are 2 nodes that are spinning up with the version 1.28.2, and in the meanwhile, the cluster is also deleting the older nodes running the older version 1.27.2. Well, after a while, we can notice that the older nodes are deleted and the newer ones are still in the updating process. This will take some time before we see them ready. Alright, so after some time, all our worker nodes are up and running, and they all are running the Kubernetes version 1.28.2, which is similar to the one running on our cluster plane node. With this, we come to the end of this demo where we saw how to perform an in-place managed node pool upgrade by cycling nodes as well as manual operation in your existing node pool. I hope you found this demo useful. See you in the next one. Thank you for watching. Hello and welcome to this lesson on configuring DNS servers for Kubernetes clusters. I am Mahendra Mehra, your senior OCI instructor at Oracle University. Let's dive in. In Kubernetes, every cluster comes equipped with an embedded DNS server for efficient name resolution. Previously, the default DNS server was kubedns. However, since Kubernetes version 1.14, there has been a transition. Now the default DNS server for the clusters created by Container Engine for Kubernetes is Core DNS. Core DNS brings modularity and extensibility to DNS management in Kubernetes. This allows for a more versatile and adaptable approach to handling DNS queries within your clusters. It's important to note that basic clusters may periodically remove customizations. If you've made specific adjustments to the default core DNS behavior, be aware that these customizations might be periodically deleted during internal updates to the cluster. During an upgrade to Kubernetes 1.14 or later, kubedns is automatically replaced with core DNS. This transition is seamless, but it's crucial to understand that customizations made to kubedns behavior won't automatically carry forward to core DNS. You'll need to create and apply a new config map with your customizations to override settings in the core DNS core file. Let's understand core DNS in more detail. Core DNS is a general purpose authoritative DNS server that is modular and pluggable. The diagram on the screen shows the components of core DNS. It runs a deployment with a default replica of 3, and for it to run, core DNS needs to access the API server, a config map to hold its core file, a service to make DNS available to the cluster, and a deployment to launch and manage its pods. All of this also runs in the kube system namespace along with other critical components in the cluster. Default core DNS behavior is controlled by a configuration file referred to as a core file. The core file is a Kubernetes config map with a core file section that defines core DNS behavior. You cannot modify core file directly. If you need to customize core DNS behavior, you create and apply your own config map to override settings in the core file. Note that with basic clusters, if you do customize core DNS default behavior, the customizations are periodically deleted during internal updates to the cluster. But with enhanced clusters, customizations are not deleted. Now let's dive into the steps to configure core DNS for your Kubernetes cluster. To begin, create a config map in a YAML file and specify the necessary customization options within the file. Here's an example structure where you define the config map. You provide the metadata information like the name for your config map, which is core DNS-custom. Namespace is kube system. And under the data field, you define all your customization options. Let's look at an example. The YAML code on the screen is a Kubernetes config map definition used to customize core DNS behavior in a Kubernetes cluster. Let's break down the key components. The API version v1 specifies the Kubernetes API version being used. In this case, it's version 1. Kind is set to config map. This defines the type of Kubernetes resource being created. And config map is used to store configuration data in key value pairs. Metadata contains information about the config map such as its name and namespace. Namespace indicates where the config map will be created. In this example, it is kube-system. Data section holds the actual configuration data in key value pairs. Key over here is example.server. and its value is a block of configuration in the form of multi-line strings. Pipe over here indicates that the following indented block is a YAML multi-line string, and the multi-line string contains CodeDNS configuration directives. Also make a note that all custom server files must have a .server file extension. Example.com specifies the domain to be forwarded, and forward.1.1.1.1 configures CodeDNS to forward DNS queries for the specified domain, that is example.com, to the custom DNS resolver, which is 1.1.1.1 in this case. Overall, this config map is creating a custom core DNS configuration by forwarding DNS queries for the specified domain to a custom DNS resolver. After defining your config map, we must apply it to our Kubernetes cluster using the kubectl apply command. Once we apply the config map, we must ensure that the customizations have been successfully applied, and you can do so using the command kubectl get config maps. Provide the namespace, which is kubesystem. Use your config map name, which is CodeDNS-custom, and use the flag -o YAML. Once you run this command, you can verify whether your settings have been applied in the config map. And to make sure that the CodeDNS reloads the config map, we must enter the command kubectl delete pod, provide the namespace, which is kubesystem, and use the label selector to delete all those pods with the label k8-app equals to kubedns. And once we run this command, the CodeDNS pods get deleted and restarted using the new configuration. Now let's explore external DNS, a powerful Kubernetes add-on that simplifies the management of DNS records for services in external DNS providers. External DNS is a Kubernetes add-on designed to automatically create DNS records for services in external DNS providers. It empowers Kubernetes services discoverability and provides dynamic control over DNS record by setting up and managing them in external DNS providers. After deploying external DNS on your cluster, you can expose a service by simply adding the external-dns.alpha.kubernetes.io/hostname annotation to the service. It is crucial to note that external DNS differs from DNS servers like CodeDNS. Instead, it acts as a configuration tool for external DNS providers. Some examples of external DNS providers include Oracle Cloud Infrastructure DNS and others. To clarify, external DNS isn't a DNS server itself, it streamlines the configuration process for other external DNS providers. Oracle Cloud Infrastructure DNS is one such external DNS provider among others. In conclusion, we've covered Kubernetes DNS with Core DNS and gained insights into custom configurations and the potential of external DNS for dynamic DNS management, setting the stage for enhanced service discovery and control in Container Engine for Kubernetes clusters. I hope you found this lesson insightful. See you in the next one. Thank you for watching. Hello and welcome to the first lesson of our multi-part series on observing Kubernetes clusters. In this series, we'll explore essential techniques for monitoring clusters, viewing work requests, viewing OKE service logs and Kubernetes API server audit logs. We'll also look at viewing application logs on managed and self-managed nodes. And lastly, we'll cover container engine for Kubernetes metrics. Now let's begin our first topic, that is monitoring clusters. Once you've created a cluster, keeping an eye on its overall health and performance is crucial. On the cluster list page, you can find a summary status for each individual cluster and its control plane nodes. The status column provides insights into the cluster's health. Let's break down the statuses. When a cluster status indicates creating, it means the cluster is being created and applications are being deployed. For a cluster in active state, indicates the cluster is running normally with control plane nodes functioning as expected. A failed state indicates an unrecoverable error has occurred and the cluster is not running. Deleting indicates cluster is in the process of being deleted and releasing resources. A deleted state indicates cluster has been successfully deleted and resources have been released. The cluster status reflects updating when the Kubernetes version on the control plane nodes is being upgraded. Remember, the cluster summary status may not directly reflect the status of individual node pools and nodes within the cluster. I'll now transition to OCI console and show you where you can check your cluster health statuses. I've already logged into my OCI console. I'll open the Kubernetes clusters service page. On the cluster list page, you can check the status of your clusters by viewing the status column. For now, as you can observe, all the clusters in my tenancy are in the active state. I'll jump back to the slide deck and continue with our lesson. Now let's shift our focus to the node pool tab, a vital area for understanding the status of individual node pools within your cluster. On this tab, you'll find a comprehensive summary of the status of each node pool in your cluster. Similar to cluster, even node pools come with various statuses, each indicating a specific state in the lifecycle of your cluster. Let's break it down. When the node pool status says creating, it indicates the node pool is in the process of being created as part of the cluster creation. Active state indicates a healthy node pool where worker nodes are running smoothly. Deleted indicates the node pool has been successfully deleted, releasing unnecessary resources. And when the node pool status says needs attention, this status signals that at least one node in the node pool requires investigation. For example, attempting to terminate a node in the pool may fail if the node cannot be drained and cordoned within the eviction grace period. It is essential to understand these intricacies for effective cluster management. I'll navigate to the OCI console and show you the location where you can check your node pool status. I'll select one of the clusters from the list. To view the node pool status, you can scroll down and click on Node Pools under the Resources section. And you can check your node pool status from the node pool status column. Moving forward, let's explore the Nodes tab, a crucial section for gaining insights into the status of each worker node within your node pool. To get a closer look, you must click on the Nodes tab, and this action will display summary status of each individual worker node. And as in the previous cases, even the worker nodes exhibit different statuses based on their current state. Let's break down these statuses. Creating indicates that the node is currently being created with the compute instance in the process of being generated. Active indicates a healthy state where the node is running normally, performing its assigned tasks. Updating is where the node is in the process of being updated, often initiated by operations from container engine for Kubernetes. Deleting means the node is undergoing deletion, releasing resources as the application is no longer required. Deleted indicates the node has been successfully deleted, freeing up all the resources. And inactive indicates that while the node still exists, it's not currently running. This can be due to the compute resource being in a status of stopped, stopping, or down for maintenance. Let's navigate to OCI console and check out the location where we get to see the worker node statuses. To check out the worker node statuses, you must click on the node pool name. Scroll down on this page, and under the nodes section you get to see a list of worker nodes present in your node pool, and the node state column indicates the statuses of your worker nodes. In conclusion, we've explored crucial aspects of Kubernetes cluster monitoring, understanding cluster, node pool, and worker nodes statuses.